Let us get started. Okay, welcome to the Pi AI slash ML workshops. We're gonna basically do a really quick rundown throughout these next couple of weeks of some basics of AI, like machine learning, deep learning, a lot of the stuff that you commonly see out there. Now, I just want to give a disclaimer beforehand that you can't really have full knowledge of machine learning and deep learning and all that in like 4 sessions. It's kind of impossible. But the point of this set of series is sort of to give you guys a basic understanding of the underlying sort of fundamentals of this area, to sort of demystify a little bit, just due to the fact that nowadays, PopSci really likes the buzzword of like ML either being sentient or being like some crazy super world destroying thing. But once you pull back the curtain a little bit, you'll see that a lot of these things are just very fundamental and simple, like not simple, I guess, very fundamental sort of linear algebra equations that are governing all of these sort of bodies. And the thing is that is really nice is you do not have to know anything about how these are computed. You'd only have to know how to apply them and sort of what they do. Because nowadays, the really nice thing about this field is that because of the usability and the practicality of a lot of these systems, companies and basically developers have made it really accessible for the average person just to apply a model or to use machine learning or AI and not necessarily have to understand exactly what's going on beneath the curtain. And to supplement that sort of idea, one thing I'd recommend is as we go through these, you are most likely not going to get like a deep understanding of everything. But the nice thing is this is such a sort of like hot field right now that you can sort of go online and just look up anything you want to know more about, and there will probably, like most definitely, be a guide talking about how to build models of a certain type or the mathematics behind certain things. So that's definitely what I'd recommend. Like if you see something throughout these presentations and you find something that you think is really interesting, go and explore that more by sort of looking it up, like checking it out, going on YouTube, looking at a tutorial, because like 99%, a lot of the stuff that we cover is going to have like deeper, like spikier stuff about it online somewhere. So yeah, now I just went through all that introduction without introducing myself. So I'm Ty, I'm a Pomona senior studying physics and computer science. And so I'll be running the next couple of these. There's gonna be, aside from this one, 3 more this semester. And they'll just cover sort of a wide range of topics, starting today with a very general overview of AI, machine learning, sort of talking about what it is and going through some of the very basic, like almost like abstract kind of view from a high level. So any questions before we get started? All right, and so throughout this whole presentation, feel free to just interrupt anytime and ask questions. So let's first just sort of start talking about what like these words actually mean. So we sort of have a bunch of different categories of things. So you have AI, artificial intelligence, and that's basically like a very broad term. It's just something artificially created that appears to behave intelligently. So just that is almost, if you view it as an umbrella, sort of the widest part. And you can kind of narrow down a bit. General intelligence, some form of artificial intelligence that can learn some set of parameters. And then we have machine learning and deep learning, which is what we're going to look more closely at today. And oftentimes you'll see the word machine learning, the words machine learning and deep learning sort of like talked about interchangeably. They aren't exactly the same thing. I mean, I will even use them interchangeably sometimes, so it'll be kind of confusing, but that's just a little side note. So to talk about a machine learning algorithm, so a machine learning algorithm is basically some sort of function with some sort of unknown parameters that is looking to solve a problem, fit some data. And the nice thing about these machine learning algorithms is if you give it a bunch of data, it can basically try and figure out a way to come up with a solution. So you don't have to have that exact solution. You're just going to have enough data and enough sort of labels of what the data ought to be to give to your model so that it can map a solution. And we're going to look at a really basic case first, which is basically the process of linear regression. So you can sort of see here on this sort of little box here, you have a bunch of numbers and you have some X's and you have some Y's. And let's look at this as a machine learning problem. We want to develop an algorithm to find some unknown y given some x. And we don't necessarily know what the relationship between x and y is, right? We are given some sort of equation, but by looking at the values here and looking at some sort of mapping of correspondence, perhaps we can develop an equation that can characterize how y, the output, is related to x, the input. And essentially, we're just fitting a function. We're fitting some sort of function where, given some known data x, the function will predict some y. And we want to evaluate its accuracy, know how well it's doing. And that, in essence, is all a machine learning model is. A machine learning algorithm is sort of something that takes in a lot of data, some sort of inputs, and then some sort of outputs. And in that middle layer, it figures out a function basically that sends these x's to these y's, that sends these inputs to these outputs. And that sort of middle layer in which it's sort of looking for this function can become very complex. And thus, this is why you have a lot of these different models that you may have heard before, like a linear regression model, a logarithmic regression model, some clustering models, and then even deep learning, which is just sort of these different methods in which we can find and solve for a function. So yeah, given some data, how do I find the parameters characterizing a function that can fit this data? So with that data above, we're going to sort of try and talk about a very basic example of this, which is linear regression. So you might have seen this. I hope you've seen this before. Y equals mx plus b, just your basic kind of linear regression equation that sends some input x to some output y. And in this instance, if we want to build some sort of machine learning algorithm that can perform linear regression, we have these two unknown variables that basically characterize the regression, right? Some slope m and some slope b. And if we were to frame this as a machine learning problem, our model is basically trying to learn the m and the b value. And by giving it a lot of data, it can sort of try to find m and the b that basically fits the data the best. And sort of, I guess, what does that mean? And this is a very, very complicated problem. Like, how do you classify data as being well fit? That is going to be a whole other section later on. And there's a lot of different ways you can quantify error in terms of machine learning. But before we sort of go there, let's just try to look at this from a very high level standpoint. So we have this set of values here, right? And if we sort of examine this data, we can see that we can basically say, well, the linear regression y equals 2x plus 1, basically we'll send our x's to our y's, right? And somehow, by giving a lot of data to our machine learning algorithm, it will be able to find those two m and b values that typically we could be able to solve for just by sort of looking through the data. So what is happening, in essence, is a machine learning model is deriving these relationships between your inputs and outputs by you feeding it a lot of data. That's the learning process, right? It'll maybe sort of, if we try to anthropomorphize it a little bit and break it down, the learning aspect is going to come from the fact that initially it might try some m and b value, and you'll look at the sort of model it creates initially, and you'll say, okay, how much error did I get? Maybe you got a lot of error. So you sort of kick the model, you say, that's a really bad job you did right there. The model will try again, and with the sort of information from the past iterations, knowing that it did a bad job, it'll try again. And it'll keep hypothetically getting better and better until it comes up with some m and some b value that will accurately fit our x and y data. So the sort of crux of these models is that they have basically trainable parameters, and it'll also try to find some best way to fit our data. And the way that I sort of like to think of it is we have this model, and we want this model to basically develop relationships between our inputs and outputs. And the main things that we can do is we can tune the sort of inner circuitry of the model to basically do the best it can, job it can for our specific circumstance. And as we sort of get deeper into this, you'll see that for certain tasks, you'll want certain models, you'll want certain parameters, and a lot of things can change based off things such as how much data you have, how complex your data you have, and the different tasks that you're sort of working on. But this is a very pretty good like mental image to have. So like sort of in summary, you have a machine learning model and you want it to find some relationship between data. You want it to have a function that'll map some inputs to some outputs. And by tuning basically knobs and buttons on your sort of mental model, it will be able to find that relationship. And how you tune it will affect the process in which that is found. And another good thing to sort of talk about is also this sort of deep learning thing is perhaps something you've heard about a lot. And if some of you guys are on project teams, it is very likely that you will be using a deep learning model. And deep learning is sort of a subset of machine learning, and it's a neural network. To sort of talk about this from a little bit more, a neural network basically being that the deep learning model is kind of modeled off a human neuron. You have like, in the sense that, like I'm probably going to say some wrong stuff about human biology, but we'll sweep that under the rug, and that you have almost like a little activation potential. And you have like a model that is very similar to how a neuron works, whether it was sort of fired or not. And these will be covered in detail later because I think deep learning is a really important topic and it does really well on complex data sets with a lot of sort of complexity and a lot of input data. But that being said, at the end of the day, even though they seem to be really awesome and can perform these really, really complex tasks, they are still just spitting a function, right? They're still just taking a set of inputs and spitting out a set of outputs. They aren't sentient robots, right? They're just really good approximators of really complex problems. And the way that they sort of do that is you'll have like higher and higher order of magnitude in regards to like how you're fitting these functions and whatnot, which is sort of, if you want to explore the more mathematical side, quite interesting, but we will not be going over that today. So answers below. All right, so we're gonna sort of go over some quick machine learning problems and solutions. And I mean, of course, you could scroll like one cell under and you'd see all the answers, but for the sake of the exercise, I encourage you not to do that. And what we're gonna go through here is basically, we're gonna have these situations and we're gonna try and figure out, are these sort of machine learning problems or are they not machine learning problems? And just to emphasize again, at the end of the day, a machine learning problem would be something where you have some input data that you want to map onto some output data. And you want to develop basically a way to fit parameters of a function to figure that out. So let's take a look. Calculating BMI from patients' heights and weights. Do we think that's a machine learning problem or not? All right, we got some yeses and some nos. So let's see. Nope, it is not really a machine learning problem. And why is that? Well, because in this case, we have a defined formula, right? We aren't exactly searching through data to like fit some sort of function. This is an exact translation. Like we know just sort of by like not really natural law, but like by our own human constructs, the way we define BMI is a fixed problem. We aren't trying to define some sort of fitted function based off some inputs or some outputs. There is an answer already, a very concrete answer. All right, let's take a look at number 2, predicting forest fires from locational data. And here we have a mixed parameter space. We got humidity, precipitation, seasons. What do you think about this one? Yes. Yes, okay. And you are right. And we see here this really differentiates from number 1 in that there is no exact quantifiable equation where I can give some humidity, precipitation, season, and I'll get some exact forest fire data. We have some sort of input data and we have some sort of output data. And the best we can do is find some best fit that quantifies it well, but we don't have an exact formula. All right, let's take a look at 3, translate between English and Spanish. What do we think about that one? Okay, so yes, so this is sort of a tricky one, right? This is, I think, could be a little bit more specific. Because if we look at sort of word level encodings, right, it's not really a machine learning problem just because every English word to an extent has a mapping to every Spanish word that's sort of defined. But when it comes to more like sort of long form translations where you have sentences and phrases and speech, then you can't simply map words one to one anymore, right? To sort of sound human and not like just some crazy translation mapping software, you have to have some sort of model that basically fits not just the words that are being spoken, but also the situation that you're in and like how casual is it, formal is it, casual? Are you speaking to like what is like the gender of the person you're speaking to? There's a lot like of a larger parameter space, and there is no sort of defined mapping or answer. All right, let's look at number 4, translate between English and Morse code. What do we think about that one? Okay, nice. So yeah, no, in this case, Morse code is just sort of a direct representation. There isn't as much phrasing or anything. We just have a way to map words onto Morse code. So yeah, in this case, it differentiates from that English to Spanish problem, and this is not a machine learning problem. All right, so what about identify the genre of songs directly from the audio? Okay, I see most people nodding. And yes, that's right. Once again, we don't really have an exact equation that'll say these audio features mean that a song is of this genre. There's a good amount of variance in this case, and we have a lot of sort of different parameters that we can use to sort of inform us on this decision. So in this case, it is a machine learning problem. What about playing tic-tac-toe? Okay, some mixed answers here. And yeah, so this is a bit of a trick question. Since tic-tac-toe is such a simple game, there is a like very concrete sort of game theory algorithm where I can say, given this move, do that move. And since the space is so small and there's a very limited amount of things you can do, you can define an exact optimal strategy for playing tic-tac-toe. Now, if we scale the game up a bit more and we introduce a lot of complexity, then yes, this will definitely go into machine learning. But in this case, because this is such a simple game and there's a well-known solution that we can basically prove is optimal, this is not a machine learning problem. And now the final question, estimate the price of a house given a picture of it. What do you think about this one? Yeah, okay, nice. So this is indeed a machine learning problem because the image features of a house and the exterior view of it may not exactly map onto a price, right? There's a lot of different factors in there. So yeah, good job, guys. A lot of these are like pretty tricky. And yeah, so there's sort of a paragraph here about talking about a lot of times it's not very clear cut, right? For instance, for like a mapping software, if we were trying to go from point A to point B and we were looking to see what's the shortest possible path to get there, let's just take this is a pretty good example for this. Like if I were to say, what is the fastest way from me to get to like the South Campus of Pomona to here? And I was say like down the street there, and I took a shortest path algorithm, right? The shortest path algorithm would basically say, oh, I just need to minimize the distance, and that'll be the quickest way for me to get there. So I'll just drive up like whatever that street is. That College? All right, cool. We'll just say that's College. You'll just drive up College, and you'll get here. That's the shortest distance. But the actual problem is a lot more complex than just finding the shortest path, right? Because the thing other things we have to consider is, for instance, traffic or stoplights. Like if it were like 2:30, perhaps I wouldn't want to take that path because students are finishing class and there's going to be like a million people crossing the street and my car won't be able to get through. And something concrete like an algorithm wouldn't be able to account for that. But if we were to give that data about like sort of how many people are going through, what the traffic is like at different hours, then we can get a machine learning algorithm that can actually find a more specific and basically like very, very complex solution to the problem. All right, so now I'm just going to give a really quick rundown of what it looks like when you have some sort of problem and you want to apply a machine learning method to solving your problem. So, all right, we have a problem. And to train our machine learning model, like I emphasized earlier, you're going to need data. And typically the more data, the better, right? For that linear regression problem, if it was a little fuzzy at first, like all the values didn't exactly fit our linear regression, if we had a lot of data, we could basically improve the certainty of the line we drew, our line of best fit, and that would allow us to develop something that fits more data. And so having a lot of data is pretty essential. And then when we sort of get that data and we develop a model, we want to see how well the model does, because there is sort of no guarantee that our machine learning model will necessarily find some exact perfect fit on our data, especially as the problems grow more complex. So it's very important to evaluate how your model is doing and to, like, as we talked about earlier, kind of tweak those things in your machine learning model to see if you can squeeze out better performance or figure out what's going on. So it's a very iterative process. And that's like the very high level view. Now we can sort of talk about a more finer grained thing. This might be a little bit complicated, so I'm going to kind of gloss over some parts of it, and you can kind of read and figure out anything you desire, like in this chunk later on. But basically, so similarly to the high level outlook, we have a problem, right? And we want to know, does this problem even need machine learning? Because sometimes, you know, you can figure out some simple algorithm that just, like our BMI problem, for instance, just maps A onto B. It's exact. We don't need machine learning. So why bother? Now, if it's not a new problem, if, for instance, you're just trying to perform something like sentiment analysis, which is a very common thing that's well known, Google it and then just take somebody else's model. Why do work when people have already done the work? So that's the next thing you should check. Now, let's say this is truly like a novel thing and you got to actually build your own model. Because, you know, already more work than we want to do. We're going to gather a lot of data yet. And we're going to actually, instead of just shoving the data into the model and praying that it does something, we want to basically manipulate the data, right? We want to clean up the stuff that'll make our model confused and give us bad outputs. We want to trim out anything that will sort of just cause like confusion between the variables and whatnot. And we want to like engineer the model, engineer the data, sorry, so that we give our model the best chance of learning the relationship that fits our data well. And oftentimes, I would note as a caveat that you don't simply want to just remove any data that isn't like clean or fits your model well. A lot of times, you might even want noisy data to put into your model. And that's so that your model can still function when you have noisy inputs. A good example of this, for instance, is the pretty controversial task of facial recognition. That's the word. Facial recognition with machine learning, right? If we just gave our machine learning model a bunch of images of like headshots, right? And we said like really perfect headshots where like a person just staring into a camera. And we said, hey, perform facial recognition, like classify maybe like what race this picture is. And we just give it a bunch of clean headshots. Well, if we stick this machine learning model on something like an airport security camera, then it's basically going to be a disaster. Now, why is that? Well, our airport security camera isn't taking perfect clean headshots of people, right? There's going to be different lightings, there's going to be different angles. And so by giving our model too pristine of a data set, we actually impact its performance and make it do really poorly on an actual realistic situation in which our data might be noisy. So you shouldn't always assume that the best data is an extremely clean data set. Okay, so once we've got our data nice and processed, then we're going to train our machine learning model on the data. And there's a lot of different models to try that we'll sort of get into later on. And then we're going to need an algorithm, and we're also going to need to iterate over our model and evaluate how it does. And a lot of the things that we talked about in the high level view are sort of kind of expanded on more. So tune hyperparameters. The hyperparameters are sort of just basically the knobs on our little model that we can turn and mess with to see how well it does. Once again, we can improve the data quality. So let's say you train a model and then you realize after it's done that it does really badly on noisy data. Well, we can just step back. We can put some noisy training data into our model and try again. I mean, we're just using software, right? There is no kind of like, oh, we built this piece of junk and it doesn't work. I guess we're screwed. No, we can just go back, tune whatever we're feeding it, and then just iterate and get another one, right? That's the nice thing about this. And of course, you can always try other models, try other training data sets, and change your architecture and see if you can eke out a bit more performance. And as we sort of go through these workshops, we're going to elaborate on like a lot of these topics a lot more. And so don't worry if sort of a lot of this just seems very broad and doesn't make much sense right now. Any questions on any of this sort of introductory stuff? Yeah, it's all right, I'll get it then. Okay, well, so we've talked for a while. We can actually look at some code now. So I just want to initially mention a couple of libraries. So when you guys see these, they don't look all too scary. So typically when it comes to machine learning, and a lot of what your project teams will be using is Python. And the reason people typically want to use Python is because it has very good library support. So instead of having to write a lot of these linear algebra algorithms or a lot of these data cleaning methods straight up by ourselves, we can just go and import some of the library and it's all built in. We just call a function and boom, we got the answer that we want. And a couple of the common ones are NumPy, which is sort of your very like well-known linear algebra library, and you can perform a lot of matrix vector operations that are pretty important either for engineering your data or just sort of playing around with models and looking at graphs and whatnot. You also have scikit-learn, which has a lot of the lower level machine algorithms like logarithmic regression or clustering just sort of built in, and you can just directly import them and just toss your data in there. You don't even have to build your model. You have TensorFlow, and as well as TensorFlow, you have PyTorch. Those are two of your like most well-known deep neural net sort of libraries, and we'll actually see an example of TensorFlow right below. And then you have Keras as well, which is sort of a higher level of TensorFlow. And what that is basically is a wrapper on top of TensorFlow that simplifies a lot of things and makes it so that you can build models really quickly with while sacrificing a bit of tunability. And I think Keras and a lot of those similar libraries are a good example of how like accessible this area is becoming, and that you can really build these things with minimal lines of code and not having to really understand much of the underlying math, which I mean, I guess is a good thing and a bad thing, but if you're just looking to apply these things, there's a lot of like easy ways to go around it. So let us actually just try and build a model. So first we're gonna install some libraries. We're gonna install, okay, let's suppress this junk. So we're gonna install TensorFlow, Keras, and all right, I'm connecting to the kernel. Probably should have done that earlier, but so we're just going to sort of import everything, and down below, after we import all these libraries, and that's pretty interesting to look through. You can see that these individual things we're importing from Keras are actually parts of a deep learning model. And you don't necessarily have to know like anything that's going on right now. This is sort of just to illustrate the fact that you can build something that sounds very complicated and sounds very elusive with a very few lines of code and very quickly. So actually, if you see in this line, we're importing different types of layers here. And we're also importing some regularizers and optimizers, which are all sort of parts of a deep learning model. Yeah, what's up? No, you'll probably have to install these libraries. You don't have them. If you're in Jupyter, this exclamation point pip install should install all the libraries that you need for the below files. But yeah, so we can run this and we can start building a model. And what's going on here? Well, we've basically defined some model architecture up there. We said we want a sequential model. We're not really going to talk about what that means, which may seem confusing, but just bear with me. And then we have the sequential model, and we're going to add different layers of the model. So we're going to add a 2D convolutional layer. We're going to add a max Foley layer, and another convolutional layer, and another max Foley layer. And what we're doing here is we're giving them like that sort of middle spot in our function fitter where we have inputs, some stuff in the middle, and then some outputs. We're basically setting up the machine in the middle that's mapping our inputs onto the outputs. And we're designating the pieces and the chunks of the architecture and that bunch of lines of code that are going to sort of transform the inputs through a function. to the outputs that we want. And the sort of things that you can tune, as we talked about earlier, in the sort of evaluation and iteration phase are things like these layers. So like maybe I want more convolutional layers, or like some different amount, like some different shape. A lot of things you can just change and play around with. And it's pretty easy to do. You can sort of just modify lines and import different things. And actually, in those 5 lines of code, we have built a machine learning model. And this may not really seem like much, but you can really tell that it is just really simple to do. And once you sort of understand what these things are doing more, I know this will just become a lot more intuitive. And you can see here, here's a model summarized. So we have some output shapes here. We have some parameters that can be trained. And you can see here that there are a lot of parameters. And this sort of model falls into the deep learning stuff. And deep learning basically is kind of one of the more complicated forms of machine learning, and it is able to do all these complex problems and to find ways to fit our inputs on the outputs because you have a lot of trainable parameters. And so imagine like basically if you're trying to fit a line of best fit, some really weird data. If you have like polynomials up to the order of like 134,000, then you probably can eke out some weird combination of exponents so that you can draw some funky line that'll actually fit your data. So that's sort of just like a pretty interesting example that we can see with like how trainable parameters show up and kind of are so complex that they can fit very like hard and difficult tasks. And we can visualize this model, and there it is. I mean, this means nothing, but this is how that model would look if we were to sort of see, this is basically the machine in the middle that's taking our inputs and the outputs. And you can kind of see that it's going to take a bunch of data of this sort of square matrix dimensionality, and it's going to spit out something that's in this like smaller little chunk. So for instance, if we were to take that earlier example of like forest fires, right? Maybe our input data would be this square matrix filled with a bunch of different values, like the humidity, like the weather and the temperature, like how many sort of animals and trees are in the area. And then here we could spit out some like single output that's like, there's a like 30% chance of a forest fire happening during the season. So yeah, I mean, that's it. You can go home and tell your parents that you built a machine learning model today, and when they ask you like what it means or how you did it, you don't really have to say anything anymore. It's all fine. But yeah, we have basically built a machine learning model. And I mean, this is very important to talk about, right? We don't really know what we just did there, right? We just put together some lines of code and something came out. And perhaps if we took some task and we used that model to apply it on that task, we could actually get good outputs. But in the process of getting those outputs, we really did not think about what we did or how we put that together and what the sort of model is doing in the middle. We just know that there were some inputs and we got outputs and it was accurate, so we're happy. But that's sort of a pretty dangerous way to think about these things, right? They're very powerful, right? They can really solve complicated problems, but they aren't necessarily flawless, and they have quite a bit of limitations. And it might seem odd to start an introductory course in which we kind of just go over really high level stuff with like why these things can be bad and terrible. But I think it's really important to kind of know about these. So let's talk about some shortcomings. So your model is only going to be as good as your data. For that linear regression example, right? If we had junk data that wasn't necessarily linear, then we would get like a bad model. So at the end of the day, you are confined to certain restrictions. And a lot of times, just because of the circumstances, you might be forced to train a model that will only have like a 60% accuracy. And you have to be sort of aware of that. Now, another thing that I haven't elaborated on much is that some of these models, that middle section in which like it actually does that process of transforming inputs to outputs, can just be a black box. Like we know it's performing some sort of operation, but we don't know what the operation is. We don't really know how it's fitting that function or what even the parameters of that function are. We just trust that it's doing well because it has good accuracy. And we'll sort of explore an example later on how that can be bad. Now, another thing is we have to be aware that these models can only do what they were built to do. At the end of the day, they're just pieces of software, right? Like if we create a model to classify a food as like a donut or like a bowl of rice, it can only do those two things. So if we give it like something else, it's going to struggle. And it should also be noted that not everything can be replaced with machine learning, because at the end of the day, like I think one example of this is that you won't ever get a model that is 100% accurate on all cases. And when it comes to things that require extreme precision, like where even like a fraction of a percent of failure rate is not tolerable, you're definitely going to have trouble when it comes to machine learning. So I think it should be noted that you can't really just approach a problem and say, okay, I need some sort of solution. Let's just shove some data into a machine learning model and then hope that we get some accurate outputs. There are definitely limitations. Another very important thing to note also is that, as we said earlier, your model is only as good as your data. And biased data can cause a lot of problems. And when we look at, for instance, a data set online that we want to download and use with our models, we have to ask the questions of who has labeled the training data? Is there bias in the labelers? What lens are we viewing this data through? Like, how are we seeing these categories and how do they relate to our ultimate outputs? And is our data varied enough, right? Like that sort of noise resilience thing I was talking about earlier, where you might have too clean of data. And a good example of this, for instance, is, once again, let's go back to that facial recognition sort of example. There's a big data set that some researchers have compiled of people's faces, and the ultimate goal of sort of model on those is to develop a thing where you give it an input face and it can detect the race of the person, right? And so this input data set has just a bunch of people's faces with the labeled race next to them. And at first, there's like a lot of pictures. And at first glance, right, you might think, okay, there's a lot of data, and that's good. We can give it to a model. Oh, and we can classify stuff. And once we test it, okay, it looks pretty accurate. We're happy. But in this case, I think there was another paper that was about this. If you looked at the sectioning of the data, you could see that actually in that data set, there is an overrepresentation of white men. And what does that mean for a model? Well, because our model is fed data that is primarily composed of white men, then it'll be really good at classifying white men, right? Because if, let's just take a really extreme example, if our model were to guess any race out of any input image, the highest way to attain a high accuracy is just to guess that the person is a white man, right? Because there are the most white men in the data set. Now, that indeed later on will cause problems, right? Because it's going to be less accurate on certain subsections of the data set. So that's just an example of why it's very important to know what's going on with your data and how the categories are distributed, because you can definitely end up having biases in certain subsets of your data when it comes to classification, for instance. Now, let's look at a little case study that sort of illustrates some of these points. The first one is about labeling animals. So let's say I build a model, right? And actually, before I go on, any questions? Okay, so let's get back into it. So let's say I'm building a model and I take some input and I want to perform a classification of these animals. I want to say, hey, model, take this image and tell me if it's a dog, a cat, a monkey, or an octopus. And I give it a big data set with labeled dogs, cats, monkeys, and octopuses. Well, all right, this model will do pretty well because let's just say it has like a 90% accuracy. If I give it a dog, it'll tell me dog, whatever. What happens if I give the model this picture, right? I mean, this picture obviously isn't a dog, a cat, a monkey, or an octopus, it's a bowl of noodles. But the model can only output whether something is a dog, a cat, a monkey, or an octopus. So regardless of what image you give it, it's going to force it into one of those categories. So if you give this as input, it'll probably say like it's an octopus or something like that. So that is one limitation. Your model is only as good as what it can output. It can't be generalized to every single thing. And let's look at another case study. Okay, so I'm going to label this the zebrafish problem. Let's build a classifier. Now, this is going to be a pretty crappy classifier because all it's going to do is tell me if something is a zebra or a fish. And actually, let's pretend you guys are the classifier. You guys are, I'm gonna show some images and you guys are gonna tell me, is that image a zebra or a fish? So, zebra fish classifiers, what is this? Anybody have any clue? Zebra, okay, nice. Okay, we're 1 for 1. Perfect. Now, what is this? 2 for 2. All right. What's this? Okay, yeah. So, I mean, zebrafish. And is that a zebra or a fish? That's a fish, right? We knew instantly that it was a fish. Now, why would this be troublesome for a machine learning model? Let's just imagine a hypothetical situation. Now, let's say we had a machine learning model and we were training it on images of zebra or fish. And it found out some way to fit a function that would find out like if something was zebra or fish. And let's say the way that this model managed to figure that out is it found that by looking at the images and seeing if they had a pixel pattern of black and white stripes, that meant that something was a zebra. And if it didn't have black and white stripes, then it was a fish. And perhaps, given the data that we gave it, that method might be really, really good and accurate, you know, because there aren't that many fish with that zebra pattern. And so what might happen when we feed it some image that is like sort of an edge case where it's a fish with that zebra pattern? Well, if the way our model recognizes something to be a zebra is just by a striped pattern, it's going to say that this is a zebra, right? And that's pretty bothersome for us because we could obviously tell it's a fish, but our model isn't going to say that. So that's the sort of black box problem illustrated right there. That's very common with deep learning models in which we don't know exactly how the model is figuring something out. And that sort of shows up in a lot of areas in which you sort of have like something that kind of straddles the edge and you don't really know how the model came to a conclusion. So you don't know what exactly it's doing. All you know is that it is accurate on some data that you've tested it on. So that's another important bias to keep in mind. So I guess in summary on this question of bias, you want to just sort of know what data you're dealing with and understand what your inputs and outputs are, build a diverse data set that's well balanced and is able to kind of like still function well with noise and, you know, test this sort of stuff. At the end of the day, you know, for models like deep learning where they're sort of black boxes, a lot of the times there might be some weird edge case that your model will never ever end up running into and you won't even figure out and everything will be fine and dandy. But I would just encourage you to kind of test your data, right? If you have some model, give it some noisy data and see how well it does. Just because, I mean, at the end of the day, we're using software, right? We have the capability to test a lot of things and just to see what behavior is like. So that's sort of just a handful of very broad points that are always good to keep in mind when you're building these things. And yeah, so that is the conclusion of this first workshop. It was then a pretty quick and very high level view of things. So if you're feeling a little confused, that's totally understandable. I would encourage, like in the future, if you want to just kind of refresh your memory, look back through this notebook and just Google anything you want to know a bit more about. There's lots of good websites and links and videos out there. But yeah, thanks for stopping, and I hope this was informative. Any questions?
Thanks, man.
Yeah.